Okay, so now we're going to be discussing about Fourier transform pairs. Now, just as a brief note, not all Fourier transform operations, such as on ones that are such as step function, for example, or a time function, will actually give us any kind of valid Laplace or valid Fourier transform. So, and actually, it turns out it doesn't matter. We don't really have to care about those Fourier transforms. There are only just a handful that, for the most part, represent a physical system. And because it represents a physical system, we're able to find a valid Fourier transform for it. Now, here are just some that we should care about. Number one, cosine of 2 pi f0t. When we apply Fourier transform, it becomes 1 half delta f minus f naught plus delta f plus f naught. This one is more of the commonly used form compared to sine. And speaking of which, here's also the representation for sine, just to kind of show you why. 1 over 2j delta f minus f naught plus delta f plus f naught. Notice that in sine, we already get a j term when it comes to the Fourier transform of it. So as such, it usually is best to avoid an imaginary number. So we always use cosine. And it turns out that cosine is one of the popular Fourier transforms due to modulation theorem. Okay, number 3. We have e to the plus minus 2 pi f naught t. And this becomes directly delta of f plus or minus plus f naught. So notice that in cosine, sine, and e to the j 2 pi f naught t, they're really related to each other with Euler's formula. Now, just in case the viewer may not be aware of Euler's formula, this is Euler's formula as given below. Okay. And then any function that is sine, cosine, or e, we can then generalize this to a time function. So this one's called the time scaling. Similar to Laplace, we can actually apply the same property. From here, it becomes 1 over absolute value of a, x of f divided by a. Very similar to how we saw it with Laplace. And just to write up Laplace, we have x of s over a. So this is the Laplace of it. And this one is Fourier. Number 5, we have time shifting. Now, similar to Laplace, time shifting is exactly the same. We have x, let's keep it general, xt plus minus t naught becomes some exponential term in the end with the same sign of 2 pi f t 2 pi t naught f, and then this becomes x of f. Once again, one of the properties in which whether you apply Fourier or Laplace transform doesn't change it. It's still the same form for the most part. Oh, and there's a j over here. Okay, so now we have a frequency shifting. A frequency shift. This is where we have some kind of e to the j 2 pi f naught t plus minus acting on x of t, and this transforms into x of f minus plus f naught. So opposite signs, essentially. Now, in Laplace, we usually kept this as e to the at when it acting on some kind of function x of t. So when we apply the Laplace, this becomes x of s minus a. Exactly the same, if anything. If we even wanted to keep it general, x of plus minus at becomes x of minus plus a. Okay, so now here are some other miscellaneous properties. So we have anytime we have a derivative, just like in Laplace, this becomes j 2 pi f x of f. Anytime we have an integral from 0 to t of x of tau d tau, this becomes 1 over j 2 pi f x of f. And then lastly, we have the most common use case with convolution. We have two functions convoluted with each other, and this becomes their Fourier transforms multiplied. And due to the duality nature of convolution, anytime we have x1 times x2 in the time domain, we have that as a convolution in the frequency domain. Now, this property is especially very useful later on for understanding modulation theorem. And that's all the important Fourier transforms that we can care about. Everything else, such as time functions, t, or polynomials, usually tend to diverge, so broadly speaking. So we don't care about them generally. They fail the kind of the sinusoidal condition. Next video, we're going to be talking about the application. And this is a field within electrical engineering of communication systems. Okay, thank you.